Okay, in this video we're going to look at the derivatives of hyperbolic functions. So we're going to do this from the basic definition. So we're going to look first of all at hyperbolic sine, which remember was e to the x minus e to the minus x all over 2. So if you differentiate that thing, you're just going to get a half e to the x, and then differentiate this bit, you're going to get a minus times minus e to the minus x, which is going to be plus e to the x. So what you get when you differentiate hyperbolic sine, this thing here is exactly the same as hyperbolic cos. So the result is, if you differentiate hyperbolic sine, you get hyperbolic cos. Really nice. So exactly the same as your sine, trig ones. Differentiate the sine, you got cos. Okay, now in this one, differentiate hyperbolic cos. So that's what you're differentiating. Differentiate the e to the x over 2, you'll get a half e to the x. Differentiate the e to the minus x over 2, you'll get minus e to the minus x. So when you differentiate hyperbolic cos, that's what you get. And that is the same as a hyperbolic sine. So this is actually easier than the trig ones, because when you differentiate hyperbolic cos, you get sine, whereas in the trig ones, you differentiated cos, you got minus sine. And that was what people always forgot, that wee minus. So much, much easier. So you've got those two results. I'll get rid of the other yellows here. There's the two results that we have. Differentiate hyperbolic sine, you get hyperbolic cos. Differentiate hyperbolic cos, you get hyperbolic sine. Easy peasy, right? So we're going to look now at how we differentiate hyperbolic tan. So this is similar to hopefully how you were showing how you differentiate regular trig tan. So you would use the quotient rule. So this means we're going to rewrite this as hyperbolic sine x over hyperbolic cos of x. And then we're going to differentiate. So just to remind us, our quotient rule, if you have u over v, where u and v are functions of x respectively, the quotient rule says it's v du by dx minus u dv by dx over v squared. And this is really easy now to do this. So our u is hyperbolic sine, our v is hyperbolic cos. So write down the v first of all, hyperbolic cos, and then du would be hyperbolic cos again, then minus, and then this is my u, which is hyperbolic sine, times my v, which is hyperbolic sine, all over my v squared, which is hyperbolic cos squared. And that top line is hyperbolic cos squared minus hyperbolic sine squared, which we know that identity now is 1. That's over hyperbolic cos squared, which is then equal to hyperbolic sec squared of x. Okay, so we have shown if you differentiate, very easy wee thing, if you differentiate hyperbolic tan, you get hyperbolic sec squared of x. Okay, next one, similar idea. Oh, I have, well, you know what, I'll just talk through this one, a very similar idea, very similar example. Same idea, you've got your hyperbolic cot we're going to differentiate here. And you can see, you write it as a quotient then of hyperbolic cos for hyperbolic sine. And then this is my v du minus u dv all over v squared. And the top line is minus 1, because it should have been hyperbolic cos squared minus hyperbolic sine squared, but it's a reverse of that. So it's going to be negative 1 over hyperbolic sine squared, which is minus hyperbolic cosec squared. So if you differentiate hyperbolic cot, you get minus hyperbolic sine, minus hyperbolic cosec. And this, I will do these ones out. These are slightly different. These are using the chain rule really more for these ones. Okay, so for this one, if you differentiate hyperbolic sec, write your hyperbolic sec as hyperbolic cos to the minus 1. Now, just be very clear, folks, that means really 1 over hyperbolic cos of x, not to be confused with this, which means the inverse of hyperbolic cos. So they're two completely different things. So this is 1 over it. So if you differentiate that using your chain rule, differentiate with respect to the bracket, you'll have minus times hyperbolic cos of x to the power of minus 2, and differentiate inside the bracket, you'll have hyperbolic sine of x, which is then, that's going to be minus hyperbolic sine of x over hyperbolic cos squared of x. and then that is the same as minus, and that would be, I'll just show my steps here, hyperbolic sine over hyperbolic cos of x, then times 1 over hyperbolic cos of x, which is the same as minus hyperbolic tan of x times hyperbolic sec of x. So that's what we get. And I'll do the other one the same way. Lovely wee examples, these ones. Using your chain rule. So here you have hyperbolic cosec. You could write that as hyperbolic sine x all to the minus 1. So differentiate with respect to the bracket, you'll have, or sorry, with respect to the power, you'll have minus 1 hyperbolic sine of x to the minus 2. And differentiate inside the bracket, you'll have hyperbolic cos of x. And then that becomes minus hyperbolic cos of x over hyperbolic sine squared of x, which is then the same as minus hyperbolic cos of x over hyperbolic sine of x times 1 over hyperbolic sine of x, which is the same as minus hyperbolic cot of x times hyperbolic cosec of x. Okay, a couple of examples on this. Fairly long video, this one, I'm afraid. Okay, what you have to do in this one is you've got to find your dy by dx. So here, you've got this, which is, we've got a mixture of trig equations and hyperbolic equations. So we've got to find our d2y by dx. So to do that, you've got to first of all find, of course, your dy by dx. This is a product, and you can see I've written the product rule at the side here. Product rule says if y is equal to uv, then dy by dx is equal to v du by dx plus u dv by dx. So here, I'm going to write down my, we can do it this way, we'll just say that's going to be, do the v first, that's hyperbolic cos of x, differentiate the cos, you'll get minus sine of x, and then we will do our u, which is just our cos, and differentiate the cosec, you'll get hyperbolic sine of x. So tidy that up a wee bit. What will we have? We'll have cos of x, hyperbolic sine of x, then minus sine of x, hyperbolic cos of x. Okay, now what we want to do then is we want to differentiate these bits. So we've got two products. So I'm going to differentiate this into a bracket, and then I'm going to differentiate this into a bracket. And hopefully I've made my brackets big enough. I'll have to maybe adjust them. So to do this then, we'll do our, we're differentiating this one first. We'll forget about the rest of it in a minute. And you'll use our product rule. So you're going to have hyperbolic sine of x times minus sine of x, and then plus, and then we'll have our hyperbolic cos of x times hyperbolic cos, that should have said cos of x times hyperbolic cos of x. That's what we've got. And then to do the next one, so we'll now differentiate this bit. So it was a minus in between these brackets. And we'll write down our v first of all. That's hyperbolic cos of x times our du, which is just going to be cos of x. And then your u, which is going to be just sine of x, times hyperbolic sine of x. And then just sort that all out. And what will happen here, let's have a wee look at this and see what will anything cancel. What will I have? I have got positive one of these, then take away a positive one of those, so they'll cancel, so they can go. And then I'll have negative sine x hyperbolic sine of x minus another sine x hyperbolic sine x. So what I actually have is minus 2 sine x hyperbolic sine of x. Lovely. Right, next example says a curve is given by the equation x is equal to hyperbolic cos of t, y is equal to hyperbolic sine of t, where t is a parameter. Find a Cartesian equation of the curve. First thing you want to do is just say x squared is equal to hyperbolic cos squared of t, and your y squared is equal to hyperbolic sine squared of t. And you know hyperbolic cos squared minus hyperbolic sine squared is equal to 1. Therefore, we'll just write that down. Hyperbolic cos squared t minus hyperbolic sine squared of t is equal to 1, which means x squared minus y squared is equal to 1. Your next thing, it says find the equation of the tangent at the point where t is equal to ln of 2. So we've got to find dy by dx. So to find dy by dx, you need to find dy by dt, and you also need to find dx by dt, and then reciprocal that and write that as dt by dx. So that's really where we're going to here. So we'll find our dy by dt first. Dy by dt first of all. Dy by dt will be equal to, if you differentiate your y there, you're going to get a hyperbolic cos of t. Likewise, your dx by dt is going to be hyperbolic sine of t. And then we'll write that out again when we had dy by dx is equal to dy by dt times dt by, dt by dx, yes. And then that is going to be hyperbolic cos of t times 1 over hyperbolic sine of t. And when you do that out, that is just going to be equal to, well, you know what, it's not really going to save you a while lot of time doing that out. And we're just going to write that out as hyperbolic cos of t over hyperbolic sine of t. So just leave it like that. That's probably the easiest way of doing it. Right, when t is equal to ln of 2, we need to find the x values and the y values and so on. So your x value, first of all, is going to be equal to the hyperbolic cos of t, which is the same as e to the x plus e to the minus x all over 2, which works out to be, I haven't left myself enough space here, which is going to be a half times e to the ln of 2 plus e to the minus ln of 2. And if you do that out on your calculator, that will become 5 over 4. Likewise, your y, which remember was hyperbolic sine of t, similar idea, is going to be a half times your e to the x minus e to the minus x, which is going to be, in this case, it's going to be a half times e to the ln of 2 minus e to the minus ln of 2. And again, if you do that out in your calculator, you will get 3 over 4. And your dy by dx then is equal to, remember it was a cos of t, which is 5 over 4, divided by your sine of t, which is 3 over 4, which works out to be 5 over 3. Okay, let's just put that into y is equal to mx plus c. So that means y is equal to 5 over 3 x plus c. And then we're going to sub in the x value and the y value. So at the point where your x value is 5 over 4 and your y value is 3 over 4, what you're going to have is 3 over 4 is equal to 5 over 3 times 5 over 4, and plus your constant. A wee bit of working out here, plus your y-intercept. Your c is going to be minus 4 over 3, and therefore your last bit, y is equal to, it's going to be 5 over 3x minus 4 over 3, and sometimes they will like that, you to multiply 3 by 3 to give you 3y is equal to 5x minus 4. So that's right, and that's right as well. Apologies for the mess there. Okay, last couple of pages. That's 3 pages in this. First one's all notes. It says the derivatives. We're looking at the derivatives of inverse hyperbolic functions. So derivatives of inverse hyperbolic functions here. So similar method as we had before. We want to differentiate this thing. So you rearrange that and you make x a subject. So xn is equal to hyperbolic sine of y. So your dx by dy will be equal to hyperbolic cos, which means dy by dx is equal to 1 over hyperbolic cos. Hyperbolic cos is the square root of hyperbolic sine squared plus cos squared. It was a positive or negative square root, but you take the positive root as hyperbolic cos. Cos of y is positive for all the y values. So that means when you differentiate your dy by dx, then it's 1 over square root of x squared plus 1. So your derivative of inverse of hyperbolic sine is equal to 1 over the square root of x squared plus 1. Similar idea for this one. If you differentiate this, you will get this thing here, 1 over the square root of x squared plus 1. So read through that bit, pause the video and read through all of that again. Similar idea. And your inverse hyperbolic tan, again, make x this thing, and dx by dy, you'll get hyperbolic sec squared. So dy by dx is equal to 1 over hyperbolic sec squared. So convert your hyperbolic sec squared to hyperbolic tan squared, and using that definition at identity, so dy by dx is 1 over 1 minus x squared. So that is what you get. So next thing, we're going to look at a couple of wee things then. Important wee identities. I think this is what the way it's given in your formula booklet, so it's very important we understand these. Get rid of those, apologies. Okay. These three wee things for us to learn, and then we'll go on from here. Okay, so if you're differentiating these, you're using your identities, the results you've just been given. So differentiate with respect to the hyperbolic sine, you will get 1 over, and it would be the square root of x, but our x, remember our angle bit is a over x over a squared, then plus 1, and there's a 1 over a on the top. So that means you can write that as, you could put that a onto the bottom line, so it's a times the square root of x squared over a squared plus 1. And then if you multiply in by that a onto the bottom line, that a comes inside, then it becomes a squared. So it's going to be the square root of x squared. Oops, sorry, that should be a minus there. Minus 1. That's going to be x squared minus a squared. Similar idea here. Differentiate with respect to the inverse of hyperbolic cos. You will get x over a squared in bottom line, and then minus 1. Sorry folks, that one should have been a plus up above there. That's a plus, apologies. And then the bottom one here, this next one is a minus, so minus 1. And differentiate the top line, you're going to get, differentiate with respect to angle, you get 1 over a. So you could write that, put that a onto the bottom line, and then that's just going to become a upon, and then the square root of x squared over a squared minus 1. And then again, that a multiplies in, it becomes a squared inside that bracket. So a squared times the x squared over a squared just gives you x squared, and then minus a squared. So that's also what that is equal to. And then your last one, differentiate with respect to the inverse hyperbolic tan, you'll get 1 over 1 minus your angle bit squared. And also differentiate with respect to the angle, you get 1 over a. So again, that is, I would just say then, we'll write that again as that's 1 over a on the top line. Bottom line, you have 1 minus x squared over a squared. And what we're going to do here is multiply top and bottom by a squared. So if you do that, you're going to get on the top line, you're going to get a. On the bottom line, you're going to get a squared minus x squared. So there we've got a few wee results. Okay, last page here coming up of our hyperbolic functions. Fantastic. So we've got a few wee results. And then we're going to use them to do this example here. If you bear with me, get rid of this. Should have this all gone already. How sloppy. Okay, Right, the results then, and I think these are the results that are given in your booklet. You've got integral of 1 over x squared plus a squared is equal to inverse of hyperbolic sine of x plus a plus c, or it is ln of that thing. And also you've got that as well, then an integral of 1 over the square root of x squared minus a squared is the inverse of hyperbolic cos, or it's equal to ln of x minus square root of x squared plus a squared. And also then 1 over a squared minus x squared dx is equal to 1 over inverse hyperbolic tan of x over a. And also you could write that one that way. So those results are given to you in your formula booklets. Okay, it says find the equation of a tangent at the point where x is equal to minus a half to the curve with equation inverse hyperbolic tan of x. So we're going to use these identities that we've been given here in the last few pages where we need to. Let's just write down what we've got here. We've got our y is equal to inverse hyperbolic tan of x, and we want to find the equation of the tangent at the point where x is equal to minus a half. So we're going to differentiate first of all, and that's just one of the ones given to us. That's what you're going to get as your dy by dx. So don't do that from first principles or anything. Just use the formula booklet and just say when x is equal to minus a half, our dy by dx then is equal to 1 over 1 minus a quarter, which is going to be 1 over 3 quarters. 1 over 3 quarters is the same as 4 over 3. Perfect. Leave it as that. Don't mess around with it. Also, when x is equal to minus a half, y is equal to hyperbolic tan to the minus 1 of minus a half. And just remember, we have got y is equal to tan to the minus 1 of x. That means tan to the minus 1 of x is equal to a half. And that's going to be ln of 1 plus x over 1 minus x, and that's in your formula booklet. Okay, and then that means you can say then this thing is just going to be equal to a half times ln of 1, and then it will be minus a half on the top line over 1 plus a half on the bottom line, which is going to be a half ln of a third. And again, to show my steps as I messed this up earlier on, that's going to be a half ln of 3 to the minus 1, which is the same as minus a half ln 3. So we've got our corresponding y value. So we're now trying to find our tangent. Tangent is, we knew the gradient was 4 over 3x plus c, and I'd just like to use y equals mx plus c. We're now going to sub in our point, which is minus a half ln 3. So that means minus a half ln 3 is equal to 4 over 3 times minus a half plus your c. And that means minus a half ln of 3 is equal to minus 2 over 3 plus c. So bring that across, that's minus a half ln 3 plus 2 over 3 is equal to your c. Therefore, last thing, happy days of our hyperbolic functions, 4 over 3, y is equal to 4 over 3 x plus 2 over 3 minus a half ln 3. So that's an exact thing. You could multiply through by, I don't know what you would multiply through by 6 to make it a wee bit prettier looking. There's no real need. That is as good as you need to go. Excellent. Thank you.